Hi everybody, welcome back. This is a video meant to accompany the notes for our energy unit. Please feel free to stop, pause, rewind the video, or fast forward if it's too easy for you at any one point in time. But please feel free to use the video to help you complete your notes. Let's begin. In the first section, which you can find in section 6.1 of your electronic textbook, it's asking us to fill out the table for gravitational potential energy, kinetic energy, elastic potential energy, otherwise known as spring potential energy, and internal energy. The first step is to begin by explaining in our own words. So let's begin. We can take a look at gravitational potential energy as the energy associated with an object's height above the lowest point. Another way you can think about it is the potential for gravity to do work. The higher you are, the more potential gravity has to do work. Kinetic energy. Kinetic energy is the energy associated with motion. Any moving object has kinetic energy. Elastic potential energy. Elastic potential energy is the energy associated with an object stretching or compressing. Could be a rubber band, a bungee cord, or even a spring. And internal energy is the energy associated with the temperature and structure of an object. Temperature is the key concept there. Now, one thing that should be noted, kinetic energy and internal energy are related. And that is because the very definition of temperature is the average kinetic energy of a molecule. What must an object have or be doing in order to have gravitational potential energy? Well, it must have the ability to fall. So in other words, it has to have some height above the lowest point in whatever the problem is. An object must be moving in order to have kinetic energy. An object must be stretched or compressed and want to go back towards an equilibrium position. And internal energy also relates to the object must be moving, because the more we're moving, the more kinetic energy we have, the higher the temperature that will be associated with it. What does it take to increase gravitational potential energy? Well, to increase gravitational potential energy, work must be done against gravity to raise the object to a higher position. What does it take to increase kinetic energy? Well, work must be done in order to speed up the object and accelerate it. Elastic potential energy? Well, work must be done in order to increase the stretch or increase the compress of the object. And what does it take to increase the internal energy? Make an object go faster. The faster it goes, the higher the temperature, the higher the internal energy. What does it take to decrease gravitational potential energy? Well, it's exactly the opposite. To decrease this energy, work must be done by gravity, not against gravity, in order to lower the position of the object. To increase kinetic energy, work must be done to slow down the object. This would be negative work. One example, of course, would be the work done by friction. Friction opposes motion, and therefore the work done by friction, the negative work done by friction, slows down an object and decreases the kinetic energy. To decrease elastic or spring potential energy, work must be done in order to lessen the stretch or compress of the object. So to increase the elastic potential energy, work must be done on the spring itself in order to stretch or compress it. In order to decrease that type of energy, now work is done by the spring in order to restore itself back to equilibrium and lessen the stretch or compress. To decrease the energy, the internal energy, work must be done in order to slow down a moving object. Slow down a moving object, the kinetic energy is lower, therefore the temperature is lower, and the internal energy would also be lower. What system possesses each type of energy? Well, this is important because this is how you relate to each type of energy. Gravitational potential energy is always related to the object and the earth. And that is because gravity is a force that is made up of two objects that are attracting each other. One object is the earth, the other object is whatever the object is. Okay, but we call it the object earth system. So if we're talking about you sitting in a chair, or let's say you on a ladder, let's say you climb up a ladder, you have the potential to fall, therefore you have gravitational potential energy. We would describe it as the person earth system, the you earth system. Kinetic energy is just found in the object. The elastic potential energy is the object spring system. Usually, when we talk about elastic potential energy, we refer to a spring. Occasionally, we'll refer to other things like rubber bands and bungee cords, but the spring is the most common device. And the internal energy is found within an object itself. Pause the video and take some time to go over this section for experiment 1, 2, 3, and 4. This is found on page 185 and 186 under the observational experiment in your electronic textbook. Okay, now that you've had a chance to do experiment 1, 2, 3, and 4 and fill out the blanks, we will go over these in class. State an equation for the work done by a force that acts through distance d, and then draw a picture in order to illustrate force, distance, and theta. And by the way, distance d sometimes will be used synonymously with displacement, and that is only because when an object moves forward in a positive direction, the change in position is the same as the length traveled. Therefore, distance and displacement get treated as the same thing and can be used interchangeably in this instance. The equation we can use is force distance times the cosine of the angle. Now, one picture of that, of course, would be if force and distance are pointing the same way. We would refer to this as a parallel force. Parallel force, theta represents the angular difference between force and distance. So if they're pointing the same way, theta is 0. Positive work would be established, and we could rewrite the formula. The cosine of 0 is 1. Therefore, this just becomes force times distance. Positive force times distance, therefore positive work. When a force is going opposite to displacement, we would refer to this as an anti-parallel force. Negative work results. Force times distance times the cosine of 180 degrees. Well, the cosine of 180 degrees is -1. Therefore, we get negative force times distance, or negative work. And then lastly, when a force is going perpendicular to the distance traveled, theta is 90 degrees between the two. 0 work is done in this instance. 0 energy change happens. Let's take a look mathematically. Force times distance times the cosine of 90 degrees. Well, the cosine of 90 degrees is 0, therefore work is 0. In section 6.2, energy is a conserved quantity in your electronic textbook, remind yourself what work does again. Again, ladies and gentlemen, feel free to pause the video at any point in time for you to reference anything for your notes. Work is the change in energy in a system. We can find the total energy by simply summing up each energy. The variable for total energy is the capital letter E. Now, there are 4 possible energies we could relate to. K stands for kinetic energy. U sub G stands for gravitational potential energy. U sub S stands for elastic or spring potential energy. And U sub INT stands for internal energy. What is a conserved quantity? Well, a conserved quantity is one in which the total amount of that quantity remains constant. Time, for instance, is a conserved quantity. We only have 24 hours in a day. If we sleep more, we have less to do when we're awake. If we sleep less, we have more time to do things when we're awake. However, we may not have enough energy to do them. Well, energy itself is a conserved quantity. As we will find out later, momentum is an example of a conserved quantity. Can the total energy of a system be changed? If so, how? If not, why? Well, the total energy can change if the work is done by a non-conservative force. For example, work done by friction. We'll get into non-conservative forces a little bit more later on. State the generalized work energy principle in a short equation and in a long equation. Well, the book describes it like this. The short equation would be the initial energy plus the work equals the final energy. The longer version would be the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic or spring potential energy plus the work done equals the final kinetic energy plus the final gravitational potential energy plus the final spring or elastic potential energy plus the change in internal energy. That is a pretty wordy way to describe an equation, and in my opinion, not the easiest way to deal with it. If it works for you, then by all means work with it. Let me propose an alternative. The alternative is not something usually described in a book, but we can describe it this way. The short way to think about work is work results in some sort of change in energy. If work is done, energy is changed. And we can see that in 3 different ways. Well, 4 different ways if we talk about changed internal energy. But if we talk about mechanical energies, kinetic and potential, work could be seen as the change in kinetic energy, or work could be seen as the change in gravitational potential energy, or work can be seen as the change in elastic or spring potential energy. The longer version of that equation starts off very short. Total initial energy equals total final energy. And as you can see, we can simply expand that. Since total energy is kinetic plus potential energy, we can expand that to say initial kinetic energy plus gravitational potential energy equals, or plus spring potential energy equals final kinetic energy plus final gravitational potential energy plus final spring potential energy. That is, of course, without friction. So what happens when a non-conservative force like friction enters the mix? It's the same equation, really. However, we have lost mechanical energy. This amount of mechanical energy is less than this amount of mechanical energy. because we have to now add and account for the work done by friction that lowered the mechanical energy after the fact. So simply adding on the work done by friction on the final side of the equation accomplishes that task. Explain why a perpetual motion machine is impossible. Well, a perpetual motion machine is one in which it is started and will keep doing work and transferring energy to the environment forever without any additional input in energy. This does not seem possible because negative work is going to be done over time to decrease the system's energy. It's inevitable. It's going to happen. So a perpetual motion machine is not possible. Something is going to slow down over time. Negative work is going to be done over time. It could be by the friction of moving parts inside the machine that slow it down. But something's going to happen in order to slow things down over time. And so think of it this way. If you don't put in any energy, you can't expect to get any useful energy or work out of a machine. We will take a look at this example in class. A bowling ball attached to a rope, swung as a pendulum, released from the position of a person's face, and swinging back to that same position. In this example, we will take a look at energy bar graphs and force distance diagrams. In other words, work diagrams. You could think of them like that. Section 6.3, quantifying gravitational and potential kinetic energies. What is the symbol for gravitational potential energy that is possessed by an object Earth system? Well, the equation we use is U sub G equals mgh. U sub G is the gravitational potential energy, measured in joules, or recorded in joules. M is the mass in kilograms. G, if you recall, is the acceleration due to gravity. Feel free to round it up to 10. 9.8 should be used for all labs, however. And H is the height above the lowest point in the problem. Consider a human body. To what part of the human body is the height measured to? Explain this in terms of a pole vaulter. Well, height is measured to what's called the center of mass of the human body. And that is because you can take a human body and you can twist it, turn it, rotate it, but the one thing that will never change about a human body is the center of where all of our mass is concentrated from. And that center of mass is going to remain at the same spot no matter how we orient a person's body. And you can see that within the pole vaulter. I'll illustrate it with blue dots. I'm going to approximate the center of mass. You can see the center of mass of the person is really what's going over the bar. You have to flip and turn and hip heist and do all these things as a pole vaulter to get over the bar. But the center of mass is really what needs to get over the bar. What is the equation for kinetic energy that an object can possess? K is the variable we use for kinetic energy, and that is equal to 1/2 mv squared. K is recorded in joules, m is the mass again in kilograms, and v is the velocity in meters per second. Work can be seen as the varying force and can be found by finding the area under a force distance graph. Area above the x-axis is positive work, meaning work done by a parallel force. Anything below the x-axis is negative work, work done by an anti-parallel force to essentially slow down the object or reduce the energy in some way. We will do this example together in class. Section 6.4, quantifying elastic potential energy. Again, please pause the video and rewind as necessary to get whatever you need for your notes. What is the equation for the force that a spring exerts on an object to compress or expand the spring? The equation is F equals negative kx. F is what's called the restoring force exerted by the spring, and it is measured in newtons. The restoring force simply means when you stretch a spring, it wants to restore itself back to its equilibrium position. Similarly, if you compress a spring, it wants to restore itself again back to equilibrium. K is referred to as the spring, or sometimes force constant, and it's measured in newtons per meter. And X is the distance the spring is stretched or compressed from equilibrium. Explain the negative that you put in the equation above. Well, the negative refers to the fact that the spring always wants to act in the opposite direction to displacement. So, for instance, if you have a horizontal spring that you're pulling to the right, the spring itself is pulling back towards equilibrium, which would be to the left. The spring is always pulling opposite to the direction of displacement to bring the spring back to equilibrium, hence the negative. What is the equation for the energy stored in a system and the spring is compressed or expanded? The equation is U sub S, the elastic or spring potential energy, is equal to 1/2 kx squared. K again is the spring or force constant, and X again is the distance the spring is stretched or compressed from equilibrium. Pause the video and try to do the test your understanding that you see here. We will go over it in class so that you can correct yourself. Now that you've had a chance to try this, we will go over it in class so that you can correct yourself. Section 6.5, friction and energy conversion. Again, please feel free to pause the video at any time to get any information you need for your notes. Write an equation for the work done by friction. Well, if work is equal to force distance cosine theta, then theta is 180 degrees because friction always opposes or acts opposite to the direction of displacement. Therefore, we would end up with the work done by friction is equal to negative force times distance. W sub F is the work done by friction, again in joules. Little f is the friction force in newtons, and d again is the displacement in meters. Now, we can also relate this to the internal energy, and here's how. When friction occurs, objects heat up. If the object heats up, its internal energy is increasing. Therefore, friction, the work done by friction, directly relates to the change in internal energy, as we see here. So if the friction force times the distance will help us get the change or the increase in internal energy. Some notes and some concepts about conservative and non-conservative forces. These were things that we saw in our energy skate park lab. The mechanical energy of a system, again, is the sum total of all your energies. So what is a conservative force? Well, a conservative force, for one thing, has potential energy associated with it. So gravitational potential energy, spring potential energy, those are examples of conservative forces. A conservative force can change kinetic energy in potential energy and potential energy into kinetic energy. A conservative force does work, but the amount of work does not depend on the path that you take for displacement, only the start and ending points. A non-conservative force is called a dissipative force, and this is one that takes energy or removes energy from the system. Scatters it, if you will. That's what dissipate refers to. Well, non-conservative forces do not have potential energy associated with them. They can change kinetic energy into heat, sound, light, any other form of energy, but not potential energy. And non-conservative forces do work on an object, but that work definitely depends on the path taken. Again, two examples of conservative forces would be gravity, which we know is the weight of an object, and a spring force. Friction and tension would be good examples of non-conservative forces. Try the test your understanding below to see if you can figure out from the graph which intervals are only conservative forces acting on the object. We will go over this in class together. Pause the video and give it a try. Now that you've had a chance to try this test your understanding, we will go over it in class to see how you did. Section 6.8, Power. Explain what power is and give a general example, give a general equation with words for power. Well, power is the rate at which energy is converted from one form to another. It's the rate at which work is done, or it's the rate at which energy changes. Rate refers to time, so all we have to do is take work divided by time. Now look a little more closely. If we take work divided by time, we know that work is force times distance. But we also know distance divided by time is velocity. So we have two equations for power. One is work divided by time. The other is force times velocity. A watt is the unit of power, and it is essentially 1 joule per second. Complete the following table to test your ability to apply power in the context of electrical energy and mechanical energy. We will go over this together in class. Now that we have concluded this section of notes, take some time for unit reflection and see what you thought, what you now know, and why you know this. Try this for 3 things that we have gone over in this video. Thank you.